Hi, hello, and welcome. I'm Greg Jacobs. I teach at Woodbury Forest School, a 1,200-acre nature preserve in Central Virginia that unaccountably includes empty dorms, sports facilities, and academic buildings. This place, normally a 400-student boarding school, is a ghost town, except for faculty families out on their daily constitutionals. I'm grateful for the continued online contact I have with my physics classes. I'm grateful for you behind the camera. Why? Because my students and you give me a goal for each day. I have important things that must be accomplished. On weekends, though, I have nothing urgent that needs my attention. No sports on television to watch. My life is goal-less. Thus, I have to create goals out of a blank canvas of a day. I can choose anything to accomplish: writing, thinking about next week's classes, planning for next school year, even watching interesting videos or reading books or cleaning the toilets. Creating goals for a day is an art, one that I'm practicing regularly. In a physics problem, the question stem proposes a situation, then you're given specific goals regarding that situation. In today's problem, for example, this spring launcher mechanism is described. Then you're told explicitly what questions to answer about that problem. Imagine, though, if the problem only described the launcher and then didn't ask any specific questions at all. Think then, not what could they ask here, because when you say they, it implies that there's a big bad consortium of enemies out there trying to trip you up. That's not true. Think, what could I figure out about this situation? One of my favorite physics teachers is Kelly O'Shea of New York City. She wrote about the goal-less problem. This is the holy grail for physics students. Given a completely open-ended situation, can you tell me all the things you could figure out? How would you figure each one out? What information do you need? How would you acquire that information from an experiment? What representations could you make to communicate your solutions? That is not just numbers, but graphs, diagrams, sentences, annotated derivations. I keep hearing the question from people, since there's no experimental question on the 2020 exam, do I have to know about experiments? I hope today that I can show you how to adapt an AP question that was explicitly an experimental design question into a goal-less problem that will help you prepare for any type of problem you might see on May 14th. Then you can use this same goal-less approach on any released AP Physics 1 or even AP Physics B exam question. When you can articulate goals out of goallessness, when you can riff on a situation using physics principles, then you are truly ready, not just for the AP Physics 1 exam, but for all levels of advanced physics. If you'd like to chime in with your thought about a goal that you could create for yourself on this or another problem, or if you just have questions, stories, or comments, @Jacobs Physics is the place to go on Twitter. I will end today's show by answering some questions from there, and afterwards I'll spend about an hour answering questions on Twitter. For now, let's go to the physics. Let's see the situation that I posed yesterday. This is last year's experimental design problem, problem 3 on the 2019 exam, and I've just started with the situation here. A projectile launcher has a spring with an attached plate, blah, blah, blah. You can push the spring back to any of 3 positions and it releases a ball and makes the ball go real fast. Well, that's interesting. I have exactly that device right here. This is one of the few physics things where I need goggles if I'm putting it anywhere near me. And that goes, zoop, there we go. And I'll probably point that away from me next time so I don't have to put these goggles on top of here. But point is, this is the launcher, the same one they described with 3 positions. So instead of asking what they asked in this problem, I want to talk about what can I figure out? What could I figure out about this? Well, given the spring constant, let's say I knew the spring constant, I could determine the exit speed of this ball. How fast is this ball going when it leaves the container? All right. Instead of using the spring launcher for that, I'm going to use a very similar device where I pull this mass down by 5 centimeters and let it go. And I want to know what is the maximum speed this thing will attain. That's the same problem, same exact problem. let's do that problem. And I want to do the other problem because in this case, I do know the spring constant of this thing. I do know the mass of this thing. That's 1 kilogram. And I told you that I'm pushing down 5 centimeters. I don't have to make that measurement. So how am I going to do that problem? Well, I'm going to use kinematics from when the ball is at rest to the exit. So its initial velocity was 0. I'm trying to find the exit speed. The displacement here was 5 centimeters, so that's 0.05 meters. I'm right here where I've pulled this spring down. I don't know the acceleration, and I don't know how long that took. Well, the acceleration, though, can be determined. I can't solve yet because I only have 2 of the 5 unknown physics variables. But I can get this acceleration because I know that the acceleration can be given by Newton's second law. I know the mass of the object hanging from the spring. And the force of a spring is kx. So let's plug that in. Combine these two equations, and I can say kx equals ma. The acceleration, therefore, is k, the spring constant of 50 newtons per meter, times x, 0.05 meters, divided by the mass of the block, which is 1 kilogram. And we multiply that out, 50 times 0.05 divided by 1 equals 2.5 meters per second per second. Put that in here. It's in the same direction as the displacement, so just everything can be upward. And we solve with Vf squared equals V naught squared plus 2a delta x, one of the kinematics equations. I know that the initial velocity is 0, so Vf equals square root of 2a delta x, which is the square root of 2 times 2.5 meters per second times delta x, 0.05 meters. And 0.50 meters per second. That is 50 centimeters per second, if I want to think of it that way. All right, let's test it out like I often do. I have a motion detector that I'm going to turn on now. The motion detector is placed directly under the vibrating object, and because it's placed in the line of the object's motion, it can make a velocity time graph. Let us do this. Velocity as a function of time. Before I collect, I have to pull this down, the requisite 5 centimeters that I said I would do. So we go from here, 1, 2, 3, 4, 5. Collect, stop, and find the maximum speed. Wait a second. Said 0.50 meters per second. I got 0.34 meters per second. Is that close? Well, not really, because that's like 50% bigger than, my prediction was 50% bigger than what I got. Wonder what's going on. My expectation is in the Twitter feed at Jacobs Physics, we got people trolling me all over the place saying, you can't do that. I hope that there are some people screaming. Brad Williams, one of the physics teachers who follows along every day, I bet you're just going nuts right now. This should grate at your very soul. Why? Because I just used kinematics in a situation where acceleration isn't constant. When we have an object on a spring, the acceleration changes throughout. Why? Because the net force is changing throughout. I found the acceleration right at the bottom. That acceleration changes as the net force changes. You can't do that. So we're going to try again. Boo. Can't use kinematics when acceleration is constant. Instead, we are going to use an energy bar chart. So once again, this is when the spring is compressed, or this is at the bottom position. This is at the max speed, and we're going to use the block spring Earth system that only has kinetic and potential energy. The kinetic energy at the bottom position is 0 because the object is not moving. I got a great question on Twitter that asked, well, wait, can't I always consider kinetic energy to be 0 on the left side of a bar chart? Because on the right side of the bar chart, I can usually consider potential energy to be 0. Nah, potential energy can be arbitrary, but kinetic energy always depends on speed. There's only kinetic energy when there's speed. So if there were speed at the bottom position, I would have to put some bars for kinetic energy. So I can see that at the bottom position, the potential energy, 1/2 kx squared, there's no work done by external forces because all the forces are internal, is equal to 1/2 mv squared, and that's the maximum speed. So I can solve for the speed, which is what I'm looking for here. There we go. There's a formula for the speed. I can plug in 50 newtons per meter. The mass is 1 kilogram. X is 5 centimeters. Plug that in here. Square root times 0.05 equals 35.35 meters per second, or 35 centimeters per second. And lo and behold, I got 34 centimeters per second. So I'm off by 3%, whereas my initial prediction was off by something like 50%. All right, moral of the story. There's nothing wrong with approaching a problem any way you can think of. Don't get stuck. Don't say, oh, I don't know what to do, because that's going to get you 0 points on any AP exam. Try something. I tried kinematics. It didn't work. It at least did something. It didn't work because I can't apply kinematics in a situation where acceleration isn't constant. So I went back and I tried again, and sure enough, energy worked. Isn't that beautiful? All right, let's go back to the spring constant problem, as you see here. I'm going to ask a different question. This is a goalless problem today. Our first goal that I created for myself was, let's figure out how to find the exit speed given the spring constant. Well, now let's go from the beginning and let's ask something that could be a paragraph question. Let's try this. A student is assigned to determine the spring constant of the launcher spring using data from the launch sphere. In a clear, coherent paragraph length response that may also include figures and/or equations, that's standard AP Physics 1 language, explain what data should be collected, how it should be collected, and how the spring constant should be determined. Okay, well, I've got an easy answer here because I already did an energy bar chart for the spring, where the spring is compressed and where the ball has its maximum speed. Let's reference that. It says that you may also include figures or equations. A paragraph problem requires sentences with subjects and verbs, but those sentences can certainly reference something that you wrote or described earlier. So I'm going to put that on my page where I have done the energy bar chart and I have solved for the speed, or I could solve for, in this case, the spring constant. If I solve for K, that gives me mv squared over x squared. So now I shall write my paragraph. The bar chart shows that in the tube, remember I wrote the bar chart over here, in the tube, spring energy converts to kinetic energy. The equation from that bar chart that I wrote over there shows that we need to know the mass of the ball, the exit speed of the ball, and the distance the spring was compressed to determine K. Notice that I didn't rewrite that equation here. I have that equation off to the side. I wrote it, I derived it. It said mv squared over x squared. So I need, right here, the mass of the ball, the exit speed of the ball, and the distance the spring was compressed to determine K. The next few sentences are going to indicate how I can determine these things experimentally. How can I determine the mass of my ball? Well, I take the ball and I place it on a scale. Plop. How can I determine the distance the spring was compressed? I take my ruler, I compress the spring, and I measure without looking down the barrel. That's easy. The harder one is, how do I determine the maximum speed of the ball? In my other experiment, I set this up because I could use a motion detector to determine the maximum speed of this thing. Why? Because a motion detector uses sound waves to determine the position of this object 20 times per second or more. And the motion detector works as long as the motion detector is in the line of this object's motion. That's not going to work here. If I take this motion detector and put it, say, here, ball's motion is here. Motion detector doesn't work to determine that speed. Could I put it up here? Well, maybe, but this motion detector or this ball is too small to be read by the motion detector. You need something at least the size of the opening here. All right, so what can I do? We got to be creative. We got to use some of the tools that you have been using in your lab all year. I keep getting asked, do I need to memorize the list of equipment that will measure force, that will measure speed, that will measure? No. Let's not think of this as a memorization problem. Let's think of this as you have done laboratory exercises in school all year. You have been watching me do laboratory exercises on these videos. You can see all kinds of other videos where people do laboratory experiments. Just think of each piece of equipment that you see on those videos or in your school laboratory as a tool. And your job is to be creative and use those tools to make a measurement that you might never have considered. So we're supposed to measure the exit speed of this ball. All right. How could we do that? A lot of ways. One thing is, what if I launch it straight up and I put a ruler in the background? I guess I might need a meter stick. I find the distance that the ball has gone up. And then I use kinematics, an unknown initial velocity, a final velocity of 0 because the ball came to rest, and an acceleration of 10 meters per second downward. That works. I could also do the same experiment, launch straight up, and I know that the energy conversion is kinetic energy to gravitational potential energy. Measure that height, convert kinetic to gravitational potential energy, and we're good. How else could I do this? What if I shot this horizontally as a projectile and found out how far this thing traveled? That would work, because now I know, if I know measure the height from which I launched the ball vertically, I know in the vertical direction that the initial velocity was 0. I know that the distance traveled was what I measured, and the acceleration was g. From that, I can determine the time it took to fall. Horizontally, there's no acceleration, so I could just use distance equals speed times time. Find that speed. That's just a standard projectile problem. What else could I do? I could take a video. Use Coach's Eye or Huddle Technique or one of these video apps, or just a good frame-by-frame video service. This thing takes 240 frames per second. So fire the thing. Video. I did this in the angular momentum problem from about 2 weeks ago, where you watch the ball go 2 frames at the beginning. Divide the distance the ball went, have a meter stick in the background so you can see that distance. Divide that distance by the time for 1 or 2 frames. That gives you an instantaneous velocity. Now, note that I can't just fire this up in the air, measure the total height, and divide this distance by time. No, velocity equals distance over time is only valid either when acceleration is 0, that is constant speed, or when we're talking about an average velocity. To find the instantaneous velocity of this ball right when it leaves, I have to find a distance divided by a time value that is very small, so it's just at that moment, or I have to use a different method entirely. Well, one more thing that I can do is I could use this photo gate that we used a couple weeks ago. Put the photo gate right here. You see, a motion detector works by being placed in the line of an object's motion. And as long as the object is in line with the motion detector and big enough, then the motion detector can give you a velocity time graph. That's great. We showed you why we can't use the motion detector here. A photo gate cannot make a velocity time graph so easily, but a photo gate can give you an instantaneous velocity. The photo gate has 2 little holes in it that hide a laser. And when the ball goes through the lasers, this thing knows exactly how long that took. I mean, to like millisecond precision. So knowing that these beams are separated by 2 centimeters, the photogate can internally divide 2 centimeters by the time it takes for the ball to travel between the beams. That's an instantaneous velocity. So I put the thing right here, fire, and this thing will spit back an instantaneous velocity. So there's a million ways to do this. I bet you've thought of other ideas. Go ahead and post them on Twitter at Jacobs Physics. But let's see how I finish the paragraph now. Now that I've just talked about a million different ways that I can measure instantaneous velocity, let's keep going. The mass can be determined with a scale, the distance compressed with a ruler. The exit speed can be measured by, look how I phrase this. I don't go on for paragraphs and paragraphs about my experiment. I just give a quick summary by a photogate placed at the mouth of the launcher. Maybe you want to include a little diagram where you put the launcher right here or the photogate right here. That's fine. You don't have to. You can just tell me. I know what a photogate is as an AP reader. Shooting the ball straight up, measuring the maximum height with the meter stick, and using kinetic to gravitational energy conversion. Notice that I don't need to do the math. I just need to say this is what I'm going to do. The problem is just asking you, how would you find speed? All right, well, that's how I'd find speed. I've communicated. Taking high-speed video with a meter stick in the background, dividing the distance the ball goes in one frame by the time for a frame. Any of those are legitimate methods. Doesn't matter, but look how I've expressed them succinctly, one sentence, so that this whole paragraph is only about 4 to 5 sentences. That's good stuff. All right, on to now the original problem. The original problem asked us, here's the setup, like we learned, same thing we did before, but now the original problem is asking us to check this hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances. That's another great question in our goal-less problem. Is the spring constant the same when I increase the compression distance? Well, it should be. That's what our textbook has said. That's what everything on our fact sheet says, is the spring constant is a property of a spring. But could we test that experimentally? Sure we can. How would we do that? Well, last year's problem gives you all this detail because they really want you to explain the detail of the laboratory exercise. That's what's not going to happen this year. It's not that there won't be a question posed in an experimental setting. Everything in physics is posed in an experimental setting. What's different about the 2020 special exam is there is no question that asks for this level of detail about an experiment. But the question, hey, how could we determine whether the spring constant is the same the whole way, is a great one. How could we do that? Well, I've got a million different answers. An experimental question always has a million different possible answers. A lot of them basically use the same approach that we've just been talking about, but I'll come up with a simple one. We solved this energy bar chart for the ball being compressed by the spring and then released at its maximum speed. So this is the equation that came out of that. And I solved for the spring constant. Constant is mv squared over x squared. So one thing we can do to find out whether the spring constant is the same is we could, here I do need to put this thing on best I can. We could compress this. I think you can see in the corner of the screen. I'll just make it up, make it nice and big. We know that formula now, that the spring constant is mv squared over x. M is the mass of the ball. That's the same every time. We could measure the speed in one of the ways that we've discussed. We could measure that speed for 3 different compression distances. This one, measure a different compression distance, which goes faster, and then measure a 3rd compression distance, where it hit the ceiling. Measure the speed each of those times. Plug that back into the formula for the spring constant that we derived and see if we get the same value within a reasonable experimental uncertainty. Better yet, since we have this equation that we derived, what if we make a plot of mv squared over x squared? Where did I come up with that? Well, because I just rewrote that to solve for the y-axis. If the y-axis is mv squared and the x-axis is the distance compressed squared, then the slope is the spring constant. If the spring constant is truly a constant for all three of these compressions, then these points will line up in a straight line, at least within whatever air bars we can create. That will be a straight line. If the spring constant is not truly constant, then we might get something like this, where we can't just draw a best fit line for all three of those things. It's always good and useful to use a graph to determine whether something is a constant value or not, or to determine an experimentally determined quantity. All right, that was the original problem. There are other ways to do that, but the best approach is to use conservation of energy like I did, and then just use one of the 5 or 6 or 7 different methods of finding the exit velocity. But now the problem asks more about the exit velocity. Let's look here at this last segment. Another student uses the launcher to consecutively launch several spheres that have different masses, one after the other. Each is launched from the same position A, so the x value is the same each time. And we want to ask, what does the graph look like of launch speed versus sphere mass? Well, once again, we have derived an equation for the launch speed as a function of sphere mass. We have derived in that energy bar chart that I'm trying to find. Here's our energy bar chart. We write that equation, and this time we're asked for launch speed, so we can, again, solve for speed. Should you memorize all these equations that I'm writing down? No. Each one of these is the answer to the specific question, or used as a tool to answer the specific question. The methodology I'm using is the energy bar chart that then becomes one of these equations. In a different situation, you'd have a different energy bar chart. But what does a graph of launch speed versus sphere mass look like? Well, we know now that the spring constant is truly constant. It's said in the problem that we are launching from position A every time. The spring compression distance is always the same. Where does mass appear? Mass appears in the denominator. So if the mass increases, the speed decreases. This is an inverse relationship. When you have an inverse relationship, a graph of those variables doesn't look like a straight line. It looks like a curve. We know that when mass increases, launch speed decreases. Well, that's the case. Mass increases, launch speed decreased. But this is always going to be a curved graph mathematically, because we know that when something is in the denominator, that makes an inverse relationship, which makes a curved graph. Now, is that accurate? What that means is, experimentally, if I launch something that is heavier with the same spring, it shouldn't go as high. Problem is, I don't have any other spheres that are a significantly different mass from that yellow one that have the same diameter. I don't have that. But, come on, Anthony, stay up there, please. I do have a different spring launcher. This one is kind of jury-rigged. I bought a compressible spring, and I'm going to push this down. And here is a small wooden ball, and well, let's do it again where I don't lose contact with it. Come on, and boom! That thing went way up high. Now, let me launch the heavier sphere. Same thing, same compression, same letting go, and that hit my hand. That was right, by the way. I'm just doing it again for you. There we go, a little higher. That didn't touch me at all. Is there any way I can get this to go higher? No. Point is, the heavier sphere, even with my best launch, only went about this high. The lighter sphere went about this high off camera, and when I did it yesterday, went even higher. I couldn't get it to the ceiling, but I could get it pretty high. Bigger mass did mean a smaller exit speed. Isn't that cool? All right. Now is the time for questions, stories, or comments on my Twitter feed at Jacobs Physics. Please go to at Jacobs Physics, and yep, Brad Williams is there, and he is telling people some answers, and I appreciate it. Could I explain the graph of mv squared by x squared again? They're confused why the slope is the spring constant, and that's Letitia. Thank you. Oh, and I like it, Letitia. You spelled out your name phonetically. I really appreciate that. Thank you. Here is that. Well, let me just do it from scratch. We started with. Yep, here we go. So you can see the camera. Letitia, we started with this energy bar chart, and that allowed us to get to this expression here, where kx, 1/2 kx squared equals 1/2 mv squared, right? So I wanted something where the slope was the spring constant. Great. We rewrite that. mv squared equals kx squared. I canceled the 1/2s. Let me write y equals mx plus b. I'm going to put mv squared on the vertical axis. I can do that because I measured the speeds and I measured the masses. Okay, I'm going to put just x squared on the horizontal axis. Why did I choose that? Well, I chose that because I could measure x, so I could put x squared on the horizontal axis. And I did that because what's left is the slope. So the slope is the spring constant. Some people prefer to do it this way, where they just solve for k. And if you have the thing you want to be your slope isolated, then you recognize that if you can graph the numerator on the vertical and the denominator on the horizontal, as long as there's no plus signs, as long as there's no plus terms, then that will give you the same result. Slope is whichever you solve for. So I hope that helps, Letitia. That's idea of writing y equals mx plus b, circling the y, circling the x, and what's left is the slope, is something that is worthwhile on in a general sense, meaning every time you're asked about the meaning of the slope of a line, that's what you should be doing. Mint 2008 is asking, are the presentations available for teachers? Well, these are available for everybody. They are online, and at the end, you're going to see a special slide that allows you to click through to all of the shows from this season. If you're interested, there are summer institutes that I do online. Just look up on my blog, and you can see those. Mint 2008, I'd love to have you at one. Nishta asks, why is the mass and the velocity curved? Could it not be negative but linear? Meaning, I'll go to my document cam again. She's asking, why couldn't the graph be like this? Because in this case, when the mass increases, the speed decreases. What's wrong with that? She says. It's a fair question. And unless I actually do the experiment for you, you're not going to see that. But what we can do is we can recognize the mathematics. Whenever we have this inverse relationship where we're graphing something versus another variable that's in the denominator, that is an inverse relationship, and an inverse relationship automatically has a curved graph that looks like this. It's a hyperbola, if you remember your math class. You don't need to know that it's a hyperbola. You don't need to know any details about the asymptotes or anything like that. All you need to know is that if we have this inverse relationship, then the graph does look like this. The only time you get this is if you have a linear graph with a slope of -1, which is very rare in AP Physics 1, although there's a couple places where it could happen, but it's very rare. If you have a denominator, then you have a graph like that. Try it sometime. This is a bad experiment to do that with because there's only 3 data points, but I do this with, for example, Ohm's law in a circuit where you can graph for constant voltage, you keep the battery the same, and you use an ammeter to measure current, and you use an ohm meter to measure resistance, or you use a variable resistor to measure resistance, and you graph I versus R. Well, that gives you this. And I do that even with my freshman conceptual physics course because once you have the equipment set up, the measurements are very straightforward, and it fills in, I mean, beautifully like that. Thank you for that question. Let's see what else we got. We still have some time. Awesome. And the question is, Lovely Butterfly is saying, would F equals KX work in this case? And I don't know which case she's referring to, but if you're asking about, could I use F equals KX to determine the maximum force on this? Yes, I could. Could I use F equals KX to determine the force to plug into F equals MA to determine the acceleration of this thing? Well, no, because F equals KX means that whenever I change my X, whenever I extend this spring, then I'm also changing the force that is applied on this object, which means that when I pull down 5 centimeters, the force is different from when this is only pulled down 2.5 centimeters. So I'm way overestimating the acceleration by using F equals KX just at one position. F equals KX does give me the force of the spring, but in order to find the speed, I need to use conservation of energy because the net force is changing and therefore the acceleration changes. Lovely Butterfly, I hope I'm answering your question. Let's see here. Can you compare, I hope I'm pronouncing it right again, and I bet I'm not. Maeve is asking, can you compare the potential energy of the spring directly to the potential energy of the ball at its top height instead of getting the instantaneous velocity? So you're just saying, hey, let's do a different energy bar chart where I use 1/2 kx squared here is equal to mgh at the top. Yes, you can. Absolutely. Just measure the height directly, and then you don't even have to find the exit speed. That works too. Absolutely, get out of the exit speed entirely. I told you there is no single answer to an experimental problem. It is when we have an experimental question or a question that references experiment, it is a creative process. It's kind of like if you're asked to write that essay that I referenced about what is the relationship between, explain the deep source of the relationship between Romeo and Juliet with textual reference. If I give that assignment to 200,000 students, I'm going to get 200,000 different answers. Many of them might be along the same lines, but I'm going to get slightly different takes on that from every one of the 200,000 students. Here, if I assign this lab question, I'm going to get 200,000 different responses. It's not like there is a rule that says every AP physics teacher must do the experiment with the spring launcher where we determine whether the spring constant is the same. No. There is no set of experiments for physics like there is for AP biology. In physics, we just need to have enough experience with the equipment in our lab that we can riff off any experimental situation, figure out how to use the equipment creatively to do whatever the problem asks, or indeed to create a goal-less problem. What could you measure and how could you measure it? Let's see, one or two more. Let's see here. Megna is asking, can you clarify what is meant by the exit speed of the ball? Is it the speed when the spring is released or after it has exited the tube? The exit velocity, the exit speed here means what is the speed right when the ball is exiting the tube. The ball, and it's easier to see here with this guy, when the spring is compressed, the ball is at rest. The ball speeds up until the ball loses contact with the spring. That's the exit speed. Then, if I launch straight up, the ball slows down. If I launch horizontally, the ball drops. Then a lot of things could happen. The exit velocity is the velocity right after the ball loses contact with the spring. And that was made clear in the last part of the problem. And finally, oh yeah, so shout out time. I was asked, let's get it here. I was asked over the weekend, Lexi wants a shout out for Mr. Petalty from Westchester East High School. And I noted that Westchester East is near Philadelphia, near the town of Westchester. That reminds me of the old PDQ Bach presenter, Peter Schickley, who claimed to be a musicologist at the University of Southern North Dakota at Hoople. And if you look at a map of North Dakota, you will understand why the University of Southern North Dakota at Hoople is wonderfully ironic. But this is Jared Mermella and his teacher Brent Shriver wanted me to watch this, or wanted him to watch this, and there's the shout out. Jared is here. Brad says I predicted his cringing because if you saw at the beginning of the show, I solved this problem using kinematics when the acceleration wasn't constant, but I did it for a purpose to show you that just because you can do kinematics doesn't mean that you should do kinematics. Nothing wrong with trying it, but it didn't work because the acceleration was not constant. And finally, people are asking, why didn't you include gravitational potential energy when I pulled this thing down in the first problem? Go back a couple lessons to where I showed the vertical spring problem. If we consider the block spring Earth system, all is one system, then the total potential energy of that system is 1/2 kx squared, as long as the x is measured from the equilibrium position, not from here. You can consider separate potential energies of the spring, where x is measured from here, and gravity, mgh, where mgh is measured from a lowest point. That's really complicated, and I don't recommend that unless you have to. When you have a vertical spring, just use the Earth spring block system and consider the potential energy to be 1/2 kx squared. That's the whole potential energy. That's the only term you need. And x is measured from the equilibrium position. And lo and behold, it worked. It gave me a 3% precise prediction of the maximum speed here. So that does work. All right. It is time. I will be on Twitter. Give me 10 minutes after this show ends, and I will be on Twitter after that for about an hour, and I will answer all your questions. Hey, please stay on Twitter with me. I'm having fun talking to y'all. Please feel free to continue to send me your responses, and I will be happy to tell you, hey, right or wrong, or here's how you would improve it. If you want to, I did not grade this problem at the reading, but if you want to find a rubric and ask me, does this make sense? I will tell you whether it makes sense. The only thing I won't do is if you say, how do you solve this problem? I'm stuck. I can't help you there. But if you show me what you've done, then I will tell you, hey, this is on the right track, or try something a little different. So let's see, things that you need to know today. I am going to do this. I'm going to turn my camera off. Don't worry, this is deliberate. I'm turning my camera off for a reason. And now I'm going to share something with you. Here it is. Thank you for watching. I want you to click this over here to subscribe for more videos. Click that circle. Click to go back to the playlist. If there's something you missed earlier on in this series of shows, you can go to the whole playlist and see Josh and me from all the way back when we started this. And you can click on the next video to continue to see other AP College Board content. It is wonderful to see everybody today, and we'll be back with you tomorrow. Josh is going to talk about the next problem, which I didn't show you, but you can. It is, I forgot to show you. Let me just tell you which one it is, and you can go find it. It is the first problem on the 2018 exam. It is about a spacecraft near Earth. It is about a spacecraft near Earth. Go to the 2017 exam, or excuse me, the 2018 exam, and look at problem 1, and it should be about a spacecraft near Earth. Just Google it, you will find it. Until then, I want everybody to come back tomorrow at noon, and I want you to say good night, Edna. Good night.